In this video, we're going to discuss torque, also known as the moment due to a force F about a point P. And basically what this is it's a measure of the tendency to rotate about P. So let's say you have some object, maybe it's long like my pencil, and we apply a force F to its center of mass, like this. Well, that's just going to have a tendency to move my pencil this way. Like a little bit later, the pencil is going to be over here, right? Well, let's change things up a bit. If my pencil is not free to move in any direction I want, but I fix one point, so I force this point to stay here, and then I apply a force F. If this point is fixed, it's going to tend to rotate about that point. This fixed point we're going to call P, and the point where we're applying the force F we'll call Q. And this measure of a tendency to rotate about the point P, which we're going to call our fixed point, is called torque. Now, torque is defined mathematically to be the cross product of PQ with F. Now, if I take its magnitude, we know how to compute the magnitude of a cross product. It's just the magnitude of that lever arm or moment arm. It's the magnitude of the vector from our fixed point out to the point of application of the force, that's PQ, times the magnitude of the force that I'm applying, times the sine of the angle between them. And I think that this makes a lot of sense. If I have a fixed point P over here and I apply the force here versus applying the force here, if I apply exactly the same amount of force, if I apply it closer to my fixed point, there's less of a tendency to rotate than if I apply the same force out here that's farther from my fixed point. So the torque is going to be larger if that moment arm or lever arm is larger. And that's exactly what we see in our formula. And of course, the tendency to rotate is going to increase as the magnitude of the force increases as well. So it makes sense that this would give us the some magnitude of this torque. This is a measure of the tendency to rotate about the point P. Now, when you take a physics class, your physics teacher probably talked to you about negative torque and positive torque. Now that doesn't really make sense with this mathematical definition of torque, but we're going to make sense of it, and we're going to see what the physicists mean when they teach you that there's positive torque and negative torque. So let's say this is our vector PQ, and we're applying a force F like this, and maybe this is 30 degrees. Now that is not the angle theta here. The angle theta is the angle between the vector PQ and F, and the angle between the vector PQ and F can be found by drawing the force vector down here so that it starts at the same point that PQ does. So they have the same initial point. I'm going to try to draw something that's parallel. It's going to be hard to do. Now if I draw that line that PQ is on, if that's 30, that means that's 30. And if that's 30, well, that means the vector, or excuse me, the angle between PQ isn't 30, it's this over here, it's everything else. And if that's a 180 degrees, and we know it is, then this is 150 degrees. So when I calculate the magnitude of the torque here, let's say that this was 5 feet. And let's say that the magnitude of the force was 20 pounds. I'm going to get the length of that moment arm, which in this case is 5 feet, times the magnitude of the force, which is 20 pounds, and then I'm going to multiply by the sine of the angle between PQ and F, which is sine of 150 degrees. And we could review our right triangle trig and see exactly what sine of 150 degrees is. It's really not that bad, but I don't want to get distracted by this. My point is that that angle that we're looking for is the angle between PQ and F when PQ and F start at the same point. So they have to be drawn tail to tail. So you can write that to yourself as a reminder. Draw F and PQ tail to tail. Or with their initial points at the same place. Same thing. It means exactly the same thing as tail to tail. Now, almost never will the picture be drawn like that. The force F is going to be drawn over here because it's being applied at the point Q. It's not being applied at the point P. But in order to identify theta, we have to move F. Okay, so now let's get some geometric intuition for why this might be true. Why this measure of the tendency to rotate about a point might be given by this. So let's look at our vector PQ again. Here's P, here's Q, and in our example, PQ is 5 feet long, and we're applying some force of 20 pounds on an angle like this. And this is obviously not to scale, that's not 30 degrees, but that's okay. Magnitude is 20 pounds. Now, I can take this force and I can split it. I can split it into two components, one that's parallel to PQ and one that's orthogonal to PQ. Let's do that. So we're finding the projection of F onto PQ. The projection of F onto PQ is this vector, and the part of F that's orthogonal to PQ is that vector. Or if I wanted to, I could just as easily draw it over here instead. So this vector plus this vector gives me my force, and this angle right here in the back, that angle is 30 degrees. Question is, well, what part of this force actually causes the rotation in the first place? Do you see that I'm losing some energy? If I'm applying this force, some of that force is pushing back onto PQ. If this is my moment arm, some of the force is pushing this way onto my pen. It's not doing the work. The part of the force that's doing the work is this part, the part of the force that's perpendicular to PQ. And you say, well, what's the magnitude of that force? Well, it's opposite 30. So we're going to get a sine of 30 right here. And we have to multiply by the magnitude. So this part of the force is the magnitude of the force times sine of 30. So now let's return to our formula. When we said our measure of that tendency to rotate was the length of PQ times the length of F, and I forgot to write it, times the sine of the angle between them, what we were really saying is, well, this tendency to rotate is proportional to the length of the moment arm. If you go farther away, the tendency to rotate is greater. So we're going to write that in here. And then we also say it's proportional to the magnitude of the force that you applied, but not just the magnitude of the force that you applied, the part of the force that acts perpendicular to the moment arm, that acts at a right angle to the moment arm. Because this part of the force is causing it to rotate. This part of the force is doing nothing. So let's think of an extreme case, a couple of extreme cases. Or actually 3 extreme cases. Extreme cases. All right. So let's say this is our moment arm. It's still 5 feet long. There's P and there's Q. And I apply a force this way, so I'm sort of pulling on it. Is that going to cause it to rotate at all? I hope you say no. The angle between F and PQ is 0. 0 degrees, 0 radians, however you look at it, that's fine. This is not going to rotate at all, and that makes perfect sense, and it's consistent with our formula. If I take the cross product of two vectors that are parallel to each other, the angle between them is 0, well then I just get 0 there. So the magnitude of the torque, or the magnitude or measure of the tendency to rotate, is 0 if the force is acting along the line that PQ is acting along. The same would be true if I went in the opposite direction. So I'm sort of pushing against my pen. Well, that doesn't rotate anything. In that case, I'll call that one F1. I'll call this one F2. In that case, I've got this, that's sine of 180 degrees, or sine of pi radians. We still get 0. So nothing's happening. If the force is acting along the moment arm, we get nothing. But let's say we're trying to be really efficient. If this is my moment arm, and I'm applying a force at a right angle to that moment arm, I'm going to get another piece of paper so that I can make it a nice right angle. Look what happens. You say, wow, that's really nice. The measure of the tendency to rotate is the length of PQ, so the length of the moment arm, times the magnitude of the force, times the sine of the angle between them, and this time the angle between them is 90 degrees, and that's 1. So now I'm not wasting any part of my force. All of my force is contributing to that rotation about that point. And that magnitude of the torque is as large as possible, because sine can't be larger than 1, right? Okay, so those are our two extreme cases. Either the force could be parallel to PQ, and we don't have any tendency to rotate, or our force is acting at a 90-degree angle to PQ, and all the force, every part of the force, is actually contributing to the motion that I want, which is this rotation, provided that P is fixed and Q is just a point on the arm that's free to move. You say, okay, well, most of the time that doesn't happen, and you're absolutely right. When we have PQ here, and we have some force over here, I'm going to draw it this way this time. There's part of the force that is a waste of energy, and part of the force that's actually doing the work. Part of the force that's actually leading to the rotation. The part that's leading to the rotation is the part that's perpendicular to PQ. So let's split this up into two parts. One parallel to PQ, so that's the projection of F onto PQ, and then one perpendicular to PQ. So on that line. Well, this is the part of F that's perpendicular to PQ. And this is the part of F that's not helping us. That's a waste of energy. You say, well, how is that related to the angle between F and PQ? Well, let's just draw F over here. So it starts at the same place as PQ. Then this angle, well, we're going to call that the angle theta, the angle between P and Q. That's the same as that angle. Okay, well, say if that's that angle, how does that relate to these two components? The one that's parallel to PQ and the one that's perpendicular to PQ. Well, the one that's parallel to PQ, well, that's adjacent to theta, so we're going to have the magnitude of F times cosine of theta. But the one that's doing the work in this case, the one that's causing this rotation, causing the rotation of PQ this way, that's this one. And that one is given by the magnitude of the hypotenuse of this little right triangle, which is the magnitude of the force of F, and it's opposite theta in the triangle, so it's sine of theta. Does that make sense? Whenever I look at my formula for torque, when I'm looking at the magnitude of the torque, the magnitude of the torque, which is a measure of the tendency to rotate about the point P, is proportional to the length of the moment arm, and then we multiply that by the component of the force that's actually doing the work. So the part of the force that's acting perpendicular to PQ. That's that right there. And then we simplify that, and that gives us a measure of torque. Now, physicists will also talk about this idea of torque being positive or negative. At least they will at TCC. Like, that's my understanding from Physics 1, Physics 2, Engineering Physics 1, Engineering Physics 2. Our professors will talk about positive torque and negative torque. As a math person, that bothers me a little bit because torque is a vector. What do you mean by positive or negative torque? That's what I think. It's the first thing that comes to my mind. Well, what they mean is, if I take this vector P, or this vector PQ, starts at a fixed point P, it ends at Q, and I apply some force F to it, that PQ and F, they form a plane. We're going to say that the torque is positive if that tendency to rotate about P, the tendency of the plane to rotate this way, or that tendency to rotate in the plane this way, we're going to say that that torque is negative if that rotation about P is counterclockwise. Or excuse me, I said the wrong thing. The rotation about P is clockwise. If it's clockwise, it's negative. So this one is negative because that is going to tend to rotate in a clockwise direction. And we're going to call the torque positive if the rotation about P, let's say this was P and this was Q, and we applied some force this way instead of applying a force that way, which would push us this way. Let's say we're applying some force this way instead. Well, that's going to pull us this way, isn't it? In that case, we're going to call the torque positive. So the rotation about P is going in the counterclockwise direction. And I think that makes sense. Just going back to trig. Back in trig class, remember when we calculated theta, we said that angle theta was positive if we went in the counterclockwise direction. It was negative if we went the other way. This is consistent with that. Now let's go to Calc 3 and say, okay, well, what does that mean in terms of this vector torque? I'm taking the cross product of PQ with F, and you're telling me sometimes that vector is negative and sometimes it's positive. It doesn't really make any sense. You're right, it doesn't make any sense. But we're going to interpret what people mean when they say this rotation about P is clockwise or this rotation about P is counterclockwise. Let's assume that this PQ and F, it's in its own plane. PQ and F are going to form a plane. Let's assume that that plane is the Z or YZ plane. So it's back here. Here's the y-axis and there's the z-axis. That's just a point in the YZ plane, back where x equals 0. Okay? And we've got PQ starting at the origin and going out to Q, and then F is over here. So PQ and F form this plane, and the plane that they form in particular is the YZ plane. You might say, Miss Townsend, what if it's not in the YZ plane? Well, we'll just change our orientation until the YZ plane is exactly where these two vectors are. So it's totally fine. Everything's relative, right? So we'll just change it. There's going to be some plane that contains those two vectors. We're going to call that the YZ plane. And the positive x-axis is coming out at us. Now I'm trying to draw that as coming out of the page, and I'm doing a terrible job. This is not in the negative x direction. This is in the YZ plane. So this is back here, like on this sort of wall. That's where that point is. But the x-axis is coming out at us. It would be more accurate to show you my pen just pointing out like this. Here's x equals 0, and there's the positive x-axis just pointing at us right now. Okay, you say, well, what do you mean negative torque? What do you mean positive torque? Well, what we mean is if P, Q, and F are back here in the YZ plane, and I'm thinking about the tendency of PQ to rotate due to F, well, I can figure out the direction of that rotation using the right-hand rule. So the torque is defined to be PQ crossed with F, and we know from the right-hand rule that means we point our fingers toward P and then we curl them towards F. Now in this picture it's not obvious that we are curling our fingers down, and we need to draw F over here so that P, Q, and F start in the same place, and then it's very obvious what we're supposed to do. We point the fingers of our right hand toward PQ and then we wrap them toward F. See how our thumb goes into the page? When our thumb goes into the page, what that means is that the cross product of PQ with F is in the direction of negative I hat. I hat comes out of the page. I hat is this way. Negative I hat is the opposite direction. It's going into the page that way. So PQ crossed with F is going into the page when, let's look at our picture, that tendency to rotate is clockwise. So when the tendency to rotate is clockwise, the physicists call that negative torque. What we mean in our class in Calc 3 is that the torque is in the direction of negative I hat. Now its magnitude is given by this. We just take the magnitude of this cross product, which is the magnitude or the length of that lever arm or moment arm times the length of F times the sine of the angle between them. That's going to give us our magnitude, and the direction is going to be given by the right-hand rule. I'll point my fingers toward PQ, wrap them toward F, and if I'm thinking of this plane that contains PQ and F as the YZ plane, if it rotates in the clockwise direction, torque is in the direction of negative I hat. And if our tendency was to rotate the other way, so if that was our force instead, so here's PQ, I wrap my fingers toward F using the right hand rule, my thumb is pointing out, and that is a counterclockwise rotation. So when it's a counterclockwise rotation, my thumb is pointing out, that means my torque, the torque vector, is in the direction of positive I hat in that case. So we say positive torque when the torque is in the direction of I hat, or the rotation about P is counterclockwise. And we say that we're talking about negative torque when the rotation about P is clockwise, or the vector torque is in the direction of negative I hat. So let's work a problem. Let's say here's P and here's Q. And it's acting, this vector PQ is, let's say, 3 feet long. This is acting at an angle of 45 degrees with the horizontal. And then we've got a force F, just pulling straight down. and the magnitude of that force, let's say it's 30 pounds. And let's say somebody is asking us to find the direction of the torque, or excuse me, well, we'll want the direction too. Find the direction of the torque. Most interested in the magnitude of the torque. What is that magnitude of the tendency to rotate? And then with the magnitude and direction, we can find torque as a vector. Okay, this is actually pretty easy. If the force is going straight down, I can draw that force over here. And we see that the angle between PQ and F is not 45, but it's 135 degrees. So using my formula, the magnitude of the torque is the magnitude of PQ times the magnitude of F times the sine of the angle between them. The angle between them is 135, so we get 3 feet times our 30 pounds of force times the sine of 135 degrees. And so we get 90 foot-pounds, and sine of 135, I believe that's square root of 2 over 2. So we get 45 times the square root of 2 foot-pounds, or we could use our calculators to get a decimal approximation of that, which we probably would because it's a physics problem. Okay, so now we've got the magnitude of the force. The question becomes, is that, or excuse me, I said the magnitude of the force, magnitude of the torque. Is that torque positive or negative? Does this force cause us to rotate in a clockwise direction or a counterclockwise direction? Well, if I'm going this way, that's clearly clockwise. So in physics class, we'd say the torque is negative, because whenever it's clockwise, we call that negative torque. So we'll say torque is negative. That's what we say in Physics 1, Physics 2, here at TCC. And then you say, okay, well, what does that mean? Well, it's in the direction of negative I hat. We can use this table, or we can use the right-hand rule again. So what is the direction of this torque? Point your fingers, use your right hand, point your fingers toward PQ, wrap them towards F. See how your thumb goes into the page? Well, that's the direction of the torque. And if we decide, if we make the choice to let this back here be the YZ plane, and we can make that choice, everything is relative. If we make this the YZ plane, then the torque is in the direction of negative I hat because it's going into the page. And so you say, what is the vector for torque? Well, if the magnitude is 45 times the square root of 2, and it goes in the direction of this unit vector, negative I hat, then the torque vector must be negative 45 square root of 2 times I hat. We just multiply those two together. And that's one way to do it. And I prefer that way because it's intuitive. It tells me, well, right-hand rule tells me what the direction should be. And then I've got this formula that gives me the magnitude. There are other ways that we can talk about this. We can get an intuitive understanding of the magnitude as well. So let's try to get an intuitive understanding of this magnitude. So we've got this vector PQ, 3 feet long. It's meeting the horizontal at an angle of 45 degrees. And this is the force vector, and it has components 30 pounds. Of course, it's not to scale. That's 30, and that's 3 feet. And you're saying, well, what does that even mean? I don't know. I don't know how pounds and feet should look on the same coordinate system. But if I want to split this force into two components, one perpendicular to PQ or orthogonal to PQ, and one parallel to PQ, I'm going to draw my force like this. Here's one parallel to PQ. That does nothing for me. And then here's the part of the force that's perpendicular to PQ. You say, well, what's that? What's that side over there? Well, if this is 45, we complete this triangle. This is 45. And if that's 45, this is the magnitude of F times cosine of theta. And this side, that perpendicular side, is the magnitude of F times sine of theta, or sine of 45. And sine of 45 happens to be the same as the sine of 135 that we got over here. So if I'm just looking at the part of F that's perpendicular to PQ, that's the part of F that's causing us to rotate about this point P. I'm just going to take this magnitude of F times sine of 45 and I'll multiply it by 3. And that's going to give me the magnitude of the torque. And so we still get 3 feet times 30 pounds times square root of 2 over 2. And so we end up with 45 square root of 2 foot-pounds, which we could approximate using a calculator. And the direction is still given by the right-hand rule. We just take that direction vector, which is 1 unit long, and multiply by the magnitude, and we get the torque as a vector. So that's one way of doing it, just with the formula. This is a more physical way of doing it, just looking at the part of the force that's acting perpendicular, because that's the part of the force that is actually causing the rotation. We can do that. So that's another way. And then the last way that you can do the same problem, and I mean, it's up to you. If you don't like either of these ways, you say, Miss Townsend, I'm not even comfortable finding that 135, or I don't like thinking about the physics, I don't like thinking about the force splitting it into two pieces. Well, then there's a third way that you could do it. You could write the vector PQ and the vector F in component form and then take their cross product, and then you could find this that way. So let's do that. So I've got this vector PQ. It's 3 feet long, and it's making this angle of 45 degrees with the positive y-axis. Well, do you see that the y component of that is just 3 times cosine of 45? And the z component is 3 times sine of 45, just using right triangle trig? I hope you do. Now, it's in the yz plane, so there is no x component. So PQ is the vector with components 0, 3 cosine of 45, those are degrees, and 3 sine of 45. And cosine and sine of 45 degrees are square root of 2 over 2, so you could just do this. 3 root 2 over 2 and 3 root 2 over 2. So we could do that. And now our force F is actually really simple. It has no x component and no y component. It's just all pointing down in the z direction. So our force has components of 0 and 0 in the x and y directions, and negative 30 in the z direction, because it's pointing down in the z direction, and we know that the magnitude of the force was 30 pounds. So you say, okay, Miss Townsend, how do I find the torque? Well, you could just take the cross product of these guys. And we should get the same answer that we got just by finding the magnitude and then using the right-hand rule to find the direction. Let's show that we get exactly the same thing. So I put I hat, j hat, and k hat in my first row of my determinant form for the cross product. In the second row, we list the components of PQ. In the third row, we list the components of F. And then let's take the cross product. So we cross out the row and column containing I hat, and we get this times this. Well, that's going to give me negative 90 over 2, so that's negative 45, times the square root of 2 times I hat minus 0. And then we're subtracting what we get when we cross out the row and column containing j hat, but that's just 0 minus 0. So we get 0 for the y component. And then for k hat, for the third component or the z component, cross out the row and column containing k hat, we get 0 minus 0 as well. So we just end up with negative 45 times the square root of 2, 0, 0, or negative 45 root 2 times I hat, which is exactly the same thing that we came up with by using the magnitude formula, and then the direction given by the right-hand rule. So whichever one you want to use is fine, but if you're asked for the direction of the torque, it should be negative I hat. That unit vector is going to be negative 1, 0, 0. If you're asked for the magnitude of the torque, you can find the magnitude this way, or you can find this vector and find its magnitude. Well, the length of a vector that goes 45 times the square root of 2 units in the x direction only is just 45 times the square root of 2. So you can find it that way, or you can find the length of that, get it that way. And then we need the vector for torque. Now you can find it by taking the direction vector and multiplying it by the length to get the torque, or you can do it this way. If you prefer the algebraic approach, it will also get you the same right answer. Now, every time you do this, you can either use this formula, or you can break the force into two parts, one parallel to PQ, which is doing nothing, and another part that's actually contributing to that rotation, and then multiply the length of PQ by the magnitude of the force that is acting perpendicular to PQ in order to get the torque. So lots of different ways, lots of different correct ways to get the same answer. And that's it. That's torque, folks.